Now let's consider what happens when we shine light through this thread grating or any other diffraction grating. Okay, we're going to let the light come out here and spread out. And it's going to come out in all directions from the two slits. And it's going to hit a wall or a piece of paper or a screen of some kind out here. Now we assume that this distance is large compared to the separation of the slits. We see that on this grating the threads are very close together. They're probably 2 or 3 per millimeter. I don't know how well you can see that. Let's bring it up close here. Yeah, well, it's a little hard to see. But the threads are wound pretty close. And if this is across the room, let's say, then this distance is a whole lot more than this distance, and we're going to get the phenomenon that we're talking about. Okay, so what do we end up seeing? The path difference here, remember, is just d times sine theta, where theta is the angle made by one of these lines, and they both make about the same angle with the line perpendicular to the grating. Okay? So we have the angle theta here that we can easily measure. If we know y out here, then that determines the angle theta. If y is the distance from this central axis to the point that we're looking at, then the sine of this angle theta is just y over r. Very close to y over r. Now this is assuming that this y is much less than r, as is the case for the dots that we see on the grating. The dots don't spread out very much at all. If we go across a 10-meter room, the dots spread out maybe a centimeter or 2. So that the distance here is going to be much less than the distance here. So the area that we're looking at, that spread out image, is going to all lie within a distance that's much smaller than the distance across which the beam travels. In that case, again, sine theta is going to be close to y over r, which means that our path difference d sine theta is going to be close to d times y over r, since sine theta is equal to y over r. Okay? Now we rearrange that to call that d over r times y, and that's your path difference. Now that path difference is usually pretty tiny, because if d over r is multiplied by this distance, what's d over r? D is the separation here, r is this distance here. D over r is a very small number because d is very much smaller than r. We multiply that very small number times y, our distance here, and we get the path difference. So if y is a centimeter, and let's say d over r is 1/10,000th or 1/1000th, then the path difference is going to be like 1/1000th of a centimeter. Okay, so very small path differences correspond to small changes in y. Now let's see how that works out. Okay, if d over r times y is a multiple, an integer multiple of lambda, then we're going to have peaks meeting peaks. We're going to have reinforcement, and that means that at that distance y, we're going to have a bright spot. If d over r times y was n plus 1/2 times lambda, we'd have a dim spot, a point between the bright spots. As y changes, d over r times y changes. And sometimes it'll equal n lambda and we'll have a bright spot, and sometimes it'll equal n plus 1/2 lambda, it'll be dim. As we move away from here, then we'll see bright, dim, bright, dim. As y changes, it changes the value of n that makes this reinforce. The distance between bright spots is then going to be r over d times lambda. Okay? If we had a delta y between bright spots, we could very easily reason from this that the delta y would be r over d times the wavelength. So if we want to find the delta y to expect, if we know the wavelength of the light, we just multiply that by r over d, which is a big ratio. We multiply the wavelength by a big number to get the separation of the bright spots. In class we observed that when delta y was a centimeter, or that delta y was a centimeter when r was about 600 centimeters, and we estimated a distance on the order of 1/10 of a centimeter, 100th of a centimeter. Now, we don't have 100 threads per centimeter, but we figured that we had a lot more than 10 threads per centimeter, so between using a 0.1 and a 0.01, we chose a 0.01. And actually, when we observed this, we were using threads that were equally spaced up here, but coming down and forming a V down here. And we were shining the laser down pretty low on the V. We weren't sure exactly what the effective distance was, but we estimated 0.01 centimeters. And what does that tell us about the wavelength? Now we know the wavelength of these lasers. I think it's about 670 nanometers, 6.7 times 10 to the negative 7th meters. But let's pretend we didn't know that and we were trying to measure lambda. Then what would our results be? Well, since delta y is r over d times lambda, our ratio r over d was about 600 centimeters or 6 meters to 0.01 meters or about 60,000. So that d over r would be 1 over 60,000 and lambda would be 1/60,000th of our delta y. Now if our delta y was 1 centimeter, and again we kind of estimated that, we didn't measure it real accurately, we get about 1.6 times 10 to the minus 5th centimeters, or 1.6 times 10 to the negative 7th meters. And that would be the wavelength of the light. That would be our estimate of the wavelength. Now that's not a bad estimate, but it's off by a factor of about 4, because the actual lambda is about 6.7 times 10 to the negative 7th meters. If we increase d to like 0.04 centimeters, 4 times as great, then d over r is going to be 1/4 as great. Instead of 60,000, or r over d, instead of 60,000, we're going to have 600 over 0.04, which will be about 15,000. So we divide the 15 centimeters by 15,000, and we get something about 4 times as great, about 6.4 times 10 to the negative 5th centimeters, 6.4 times 10 to the negative 7th meters, which corresponds real closely to the 6.7 times 10 to the negative 7th meters that we observe here. Now just briefly, a couple of diffraction phenomena that we can observe. If we have 2 plates of glass separated by a hair, let's say, and we're exaggerating the angle here, and we're looking at light that's coming in and bouncing off of this system. The light that comes in here could bounce off of the first plate of glass and come to our eye, or it could pass through the first plate and bounce off the second and come to our eye. And we're going to get some of both. And since the light isn't that much diminished, we're going to get about equal amounts of both kinds of light coming in. Now what does that do? Well, depending on how much extra distance the light here travels between the 2 pieces of glass, we might have reinforcement, we might have negative reinforcement, we might have bright or we might have dim. As we look at different points along here, we're looking at different path differences, and sometimes the light that reflects off the first plate is going to reinforce the light that reflects off the second, and sometimes it's going to tend to cancel, and we're going to see alternating bright and dark lines as we look across here. If we look at an oil slick, okay, now this depicts a smooth surface of water, there's a shark's fin, and an oil slick, a very thin oil slick along the water. If light comes in here, it could bounce off the top of the oil slick, or it could go through the oil slick and bounce off the water. That creates a path difference. Now that path difference might correspond to a whole number multiple of, let's say, blue light or red light or orange or green or whatever. The wavelengths of different colors of light are different. So that at a point where this thickness here creates a path difference that reinforces, let's say, blue light, you're going to see predominantly blue. At a point over here where the path difference reinforces red light, you might see red. So you're going to see bands of color, kind of rainbow colors, on an oil slick, and that's something, of course, that you do observe.